Good morning, everyone. Today, let us see Boolean arrays and masking. Basically, Boolean arrays and masking are commonly used for filtering data based on conditions. Generally, we apply data filtering using multidimensional arrays. They are used in various array operations where element-wise selection or modifications are required. Further, we will also see fancy indexing, useful for advanced indexing operations like selecting specific element from an array based on complex criteria or pattern. These are fundamentals in array programming and are extensively used in data manipulation and data analysis. Boolean arrays, masking, and fancy indexing are covered in this session 7. In array programming, using Python, Boolean arrays are arrays consisting of Boolean values, true and false. They are often used to filter or select elements of arrays on certain conditions. Let us explore the uses of Boolean arrays with the help of masking and fancy indexing. This session covers the use of Boolean masks to examine and manipulate values within Numpy arrays. The masking comes up with when you want to extract, modify, count, or otherwise manipulate values in an array based on some criteria. For example, you might wish to count all values greater than a certain value, or perhaps remove all outliers that are above some threshold. The Numpy Boolean masking is often the most effective way to accomplish these type of tasks. There are many universal functions in Numpy library to compare and manipulate the arrays using masking and fancy indexing. Let us see the comparison operators with the help of Numpy universal functions. In computation on Numpy arrays, universal functions we introduced in the previous session focused in a particular set of operations like arithmetic operations. We also have seen the arithmetic operators like plus, minus, multiplication, division, modulus, and so on under arithmetic operators, and other important array operators on arrays leads to element-wise operations. Numpy also implements comparison operators such as less than, greater than, less than or equal to, greater than or equal to, not equal to, the 6 standard comparison operators. The result of these comparison operators is always an array with a Boolean data type. It returns true or false. All 6 of the standard comparison operators have an alternate universal functions under Numpy library. Now let us see how Boolean arrays are generated on a condition. Here I have created 2 arrays, array 1 and array 2 with the values, 5 elements in each array. You can observe I just wanted to compare array 1 with 3. array 1 less than 3 will return the true or false of the value comparison. As we know, these universal functions shall be applied on every element of an array. Array 1 less than 3 is a relational operation on an array, returns a Boolean array. Every element of an array is compared with the scalar value 3 and then returns true or false based on condition. Now 3 is, see, if you take a array 1, 3 is, 1 is less than 3, the first element. Okay, that's what it is true. The second one is also true. Whereas 3 is not less than 3, it's a false. And 4 is not less than 3, it's a false. And 5 is not less than 3, it's a false. Now you can simply observe it have written a Boolean array. Or simply an array with a condition returns you Boolean array. You can also apply greater than, less than or equal to, greater than or equal to, not equal to, and equal to. You have an alias. These symbols works as an alias to universal functions. We have a set of universal functions available under Numpy library. These functions are np.greater. We'll compare element wise. We'll compare element wise in both the arrays, array 1 and array 2, and returns true or false. You have a np.greater than, equal, underscore equal, np.less, less than will be represented np.less, np.less underscore equal, np.equal, np.not equal. And not only this, you also have the other comparison operators such as logical AND, logical OR, and logical exclusive OR. Just as in the case of arithmetic universal functions, this will work on arrays of any size and shape. You can apply on multidimensional arrays. Let us see an example. Here, I wanted to generate a random object for which I am using random state, which actually creates a random number generator. This object further can be used to generate the random numbers, iterable random numbers. So if you run this, you'll get 3x4 shaped matrix from 1 to 10. And if you just simply put a condition x less than 6, this condition is applied on every element of an array without explicitly specifying the index position of element in an array. This is the biggest advantage of Numpy. Now you can observe when I run this, it returns a Boolean array where it consists of true and false elements. Where the condition is true, it represents a true. Where condition is a false, it represents a false. This true is 1 and false is referred as 0 in Boolean arrays. In each case, the result is a Boolean array. And Numpy provides a number of straightforward patterns for working with these Boolean results. Now, working with Boolean arrays, given a Boolean array, there are a host of useful operations you can do. We'll work with an array X, the two-dimensional array, as we have just created above. Now, you can see these are the elements of an array X. Let us find how many non-zero elements in the given array. Not only that, I just wanted to find non-zero elements on a condition. To count the number of true entries in a Boolean array, we have a universal function called count underscore non-zero, and you can pass the Boolean array as a argument. X less than 6 returns Boolean array. It returns a Boolean array. Now I am passing this Boolean array as an argument to count underscore non-zero universal function. Now we can observe how many truths are there. 1, 2, 3, 4, 5, 6, 7, 8. So when you run this, you get 8 as an outcome. That's how you can simply count non-zero. Here in the non-zero is not, zero is not actually a quantity. The zero indicates what? The false. Non-zero say it's a true. Got it? If you simply do this, now you can observe. See, it is on direct element X, I mean array X. So how many elements you have totally? 1, 2, 3 into 4, 12. Out of 12, how many are non-zeros? 11. Now, in this case, count underscore non-zero of any condition you can. Any condition you can give. For suppose I wanted to find the values above 6. Now you can see there are only 3 values. That is what is 7, 9, okay, and 7. There are only 3 values that are greater than 6. So your Boolean array has only 3 truths for this X greater than 6. How many truths you have? 1, 2, and 3. So that's how we can simply count the true entries using non-zero universal function. Got it? Now we see that there are 8 array entries that are less than 6. Now you can observe, you can also count them. Okay, it's an alternate way to count by using sum. Of course, you have to be very careful when you are using the sum. The normal sum is different than the Numpy sum that we have already seen in the previous session. Now you observe what I wanted to do is I wanted to sum the Boolean array ones. What are the Boolean array ones? Now you can observe what I did is I took a greater than. Now how many I got? 3. So basically, when you say false represents zeros and then one represents true, then how many truths are there? 3. So the sum of all these things, 3. It's not the count. But finding a count can be also done using NP sum. Right? Now, see, the biggest advantage of this sum is, what is the biggest advantage of the sum? It helps us to navigate to every element of an array, right, along with the rows and columns. And now you can also find the sum along with the axis. If you wanted to find row-wise elements horizontally, you can use axis is equal to 1. As I said in the last session, 0 indicates rows, 1 indicates columns. When I say axis is equal to 0, what happened? It's a column. Sorry, it's a row, but the operation will be performed vertically. All right. Now you can see. You can see x less than 6. How many are there? X less than 6 means less than 6 elements in the first column. When I say column, it is vertically. All right. In the first row, first element. In the second row, first element. Third row, first element. You have got 2. Similarly, vertically it does. Right. And then now you can see. You can observe when you perform vertical operation, then this is the case. For suppose, if it is a column axis, but you measure horizontally. Now you observe, when I say horizontally, it takes all the elements, the 4 columns of a first row, right? So now you can observe the first place, all of them are less than 6. Second place, 2 of them are less than 6. In third row, 2 of them are less than 6. This is how it works on Boolean array. They arrive the condition, returns a Boolean array that can be used as an index, right? So you can also count the number of values less than 6 in each row of the matrix, and you can also use the other important universal functions like np.any or np.all. When you take np.any, if there is any value that meets the condition, then you will see true, else false. Now you can see. For suppose if I use 6, now you observe how many elements, how many elements are 6 values. Now you can see print. Now you can see I have only 1. Let me take 3. Now how many are there? 1, 2, 3. So in this condition, it returns 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0. That's what is true or false, I simply mean to say. Right? So simply, if it has at least a 1, any one of the element returns a true, then it is true. Right? First, suppose let me take some 10. Now it's false. There is no such element. So none of the element is matching with the 10, then all the values are false. Then it's false. Understand? So similarly, you can apply. And let us see the all. If all the elements of an array are matching with the condition, then it returns true. If any one of it is false, then it's false. Right? So you can take a condition. None of the element is less than, greater than 10 or 10. So all the elements are less than 10 in the given array X. Then it returns. If I wanted to just check, all are equal to 10, but none of them, it returns false. You can also use axis parameter to perform this any or all operations along with axis. Or suppose in your array, if you wanted to perform an operation to compare the elements with 8 along with columns horizontally, you can use axis equal to 1. Now you observe. What happening? What is the role of all? If all are true, it is true. If all are true, it is true. Otherwise, not. Then you can see when I give axis equal to 1, what does it mean? What does it mean? It is a column in horizontally. A column. Columns are considered horizontally row wise. So the row, what is the first row? 5033. None of them are what? Above the 8. So all of them are less than 8. Then all are true, then it is true. Next, horizontally. Now you can see one of it is not meeting the condition. Then false. It's a true, false, true, true. Then one of it is false. Then all are not true. Then it is false. Next, all are less than 8. Then it is true. Okay. Now you can see these Boolean operators. We have already seen how we might count, say, all the elements matching a value, etc., using comparison operators. But if we want to know about all the elements with a condition, this is accomplished through Python bitwise logical operators. There is a difference between the symbols like ampersand, pipe, okay, caret, and then tilde symbols, like with the other standard arithmetic operators. Numpy overloads these as universal functions, which works element-wise on any dimensional array. All these symbols have an equivalent universal functions in Numpy, such as NP logical AND, logical OR, logical XOR, that is exclusive OR, and logical NOT. For example, we can address this sort of compound questions as follows. What I did is, I took two Boolean arrays. Of course, I can generate the Boolean arrays by doing comparison using either arithmetic operator, okay, arithmetic operations, and then I can do any operations, but if it has any condition with a one relational operator, then that is treated as a comparison, isn't it? So if I use any comparison operator, it returns a Boolean array. Instead of that, directly I'm taking a Boolean array for easy calculation. I took two Boolean arrays. One is array 1, Let me call it the Boolean array 1 and Boolean array 2. All right. The logical AND results. I just wanted to pass the Boolean array 1 and then Boolean array 2. It does the logical AND operation. When you say logical AND, what is the result? If all are true, it is true. Otherwise, false. As simple as. Now, if I go to logical OR, then if either of the one is true, then it is true. Coming to the exclusive OR, what is the exclusive OR? Tell me what is the exclusive OR? If both are same, it is false. Okay. If both are same, it is false. Otherwise, it is true. Right? I mean to say, if all are true, it is false. If all are false, also it is false. Okay. And then if logical or not is a simple negation. If it is a true, it is false. If it is a false, then it's a right. Now, what we can do is we understand how to generate Boolean arrays by using comparison operators in Numpy. These Boolean operators can be used as the masking index. What do you mean by masking? As I told you, the Boolean arrays are arrays consisting of Boolean values like true or false, and these shall be used as an index. This masking involves using Boolean arrays to select elements from an array. It is essentially the process of applying a Boolean array as a mask to another array to extract or modify certain elements. It's not so difficult. It is almost related to Boolean arrays, and then oftenly we use them without explicitly mentioning a masking. We use the Boolean arrays as an index. Instead of simply giving an index positions, we can also give a Boolean arrays as an index where these Boolean values masks the original elements. They only say conditionally it is true or false. That's what. This is a more powerful feature of Numpy arrays. Okay. So let us see on our example. There is an array X, and then let us see how we can apply masks on arrays using Boolean values. Now this is my X, and then now we have already seen, and then when I put a condition on X, it compares element wise and then returns true or false. All right, now you can observe what I'm passing is I am passing that Boolean array as an index, which is known as mask. I'm not actually mentioning the positions of the positions of elements in an array. Instead, I'm passing the Boolean array of a particular array as an index so that it considers the true positions as references. In this case, you can simply observe This less than 5 returns false, true, 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 false, true, true, like this. Now you can also observe. Let me also print X here. Print X. Now you observe where there is a true return. So that is the consideration for your mask. Now here false, it doesn't consider. True is 0, 0. That's what a 0 is displayed. Next one is a 3 is true. And then this is also true. Then these 3 are displayed because these are true, because they are less than 5. And then this is false, this is false. That's what these are not printed. And this is true, another 3. 5 is not less than 5, then it is false. And then these 2 are true. And then 7 and 6 are false. That's what it returns. 0, 3, 3, 3, 2, 4. All right. So this is how we can use the mask to select elements from an array indirectly. What is the advantage? What is the advantage? You can apply any condition and simply filter the elements. So when you work with a huge data, filtering elements are very much important and crucial for manipulations, the data analysis. All right. Now let us also just see what is mask and what is an array. So when I use mask, I mean to say I'm using a Boolean array as an index, right? And then my array on mask is, it's important, it returns not in the original index form, it returns in mask form. Got it? It's very important. Our actual X is a 2-dimensional, whereas the return value is not. So it follows a mask pattern rather than original matrix form. So not only this, using the keywords like and, or, and then other are also very important. But you can see there is a slight difference between using logical and logical or, and the single bitwise operators like and pipe symbol, ampersand and pipe symbol. One common point of confusion most of the times we have is keywords like logical and or, and then a bitwise operators, ampersand and symbol, and then pipe symbol. The difference, what is the major difference? The major difference is this logical and or usually returns an object. Okay, the works on the entire collection. That's an array. Whereas your ampersand and pipe symbol works on bits. When I say bits, they are not elements of an array. Okay, bits means an elements in binary form. Okay, and probably it depends upon the size of the element. If it's a 4 bytes, it's represented in 4 or 4 into 8, 32 size. So like that. Okay, let us also see a few examples how they are different. Now you can see I wanted to know the Boolean value of 42, and then when I say Boolean, and it's true or false. I already said the Boolean 0 indicates what? False. The Boolean 1 indicates what? True. 1 or any positive value. All right. Now I can perform some logical operation between these Boolean objects. Now if I perform 42 and 0, it's a true, and 0 is false. If you use OR, it is true. Now, let's also observe the bitwise and OR operators. Now, let me take smaller values for easy understanding. I took 5, and equivalent binary representation is 101, and then a binary representation of 4 is 100. This is pretty easy to follow, right? Now you see, if I perform logical, bitwise or between 5 and 4, what it returns? It's a bitwise addition. Okay. Now you can see 1 and 0 is a 1, 0, 0 is a 0, and 0 or 1 is on either of the one is true, it is true. That's what I got. It is 101. If you use AND, if both are same, then both are ones, then only it is 1, otherwise 0. That's what I got. 1, 0, 0. What the difference? What the difference? So a logical AND or exclusive or not, all this works on object, whereas the bitwise operators like ampersand, okay, or symbol pipe, right? This works on bitwise elements. Right? Now, instead of taking true or false, we can also take 1 or 0. But you have to explicitly mention the data type. Otherwise, what happens? By default, it considers them as float values. We all know that. Unless we explicitly specify the data type, by default, it considers a float type and the numeric values. Now here, since I wanted to, instead of saying true, false, and true, false, I just wanted to give 1 or 0, and then 1 and 0 represents true or false in Boolean data type, as we have seen earlier. So that's what, when I am defining my array, I am defining it as a Boolean type collection, right? So then now I can simply perform any bitwise operation between these elements. All right. Now let us check. Can we apply the logical operation between the Boolean values? It's very difficult. Why it is difficult? As I told you, these logical and logical OR operations shall be performed on an entire object where A and B are now not possible. You cannot apply on the entire one at one go. A should be only one, true or false, or B should be true or false. Then only it is possible to apply. It should be one value, reduce it to one Boolean value. Then B should be reduced to one Boolean value. Then only it is possible. Understand? But I can use this operator or this operator between A and B because this works on elements bitwise. What the difference? You cannot apply logical AND and logical or logical exclusive or logical not, all these operations on bits because the logical operations expect only true or false, a single object. Got it? That's where you cannot use these logical operators. So the truth, now you can see the value error. The truth value of an array with more than one element is ambiguous. More than one element is there. So what we can do? We can do again a Boolean array. We can again measure the Boolean array outcome, any or all, will return what finally? True or false. Okay, true or false. Then between them you can apply logical operations. Okay, so you can apply. Now you can observe. What I did is I just took the same x, right? Print x. Now you observe my x is what is 1, and then what I did is, now you can observe when I perform this, I'll get what? One Boolean array. If you want, you can check it. Okay, and you can also take right. What happened? Now you observe this is one Boolean array you have got, and this is another Boolean array. Whatever, it's easy understanding. I'm just giving you space. Okay. Right now you can see, and for my first condition, I've got this, right? A Boolean array. For the second condition, I got another Boolean array. Now you can observe these are bits. This acts as what? But guess what I can perform? Between true and false, I can perform logical operations. But it's a collection. Whereas you can observe, I cannot perform element by element Boolean operation. So what I have to do, I have to get only one true as a result of this, but it's an array, not a single true or false. Similarly, it's not a single true or false. That's what I got an error. And what is the solution? np dot all. If all elements of an x are greater than 4, then it returns true, only single true. If any one of it is not greater than 4, then it returns false. Similarly, I can also use np dot any. Now you can see I can do this, right? So let's stop it here, and then we'll continue how we can use this masks as an index to an array, and how we can also use slicing to filter the elements based upon Boolean arrays and then Boolean values in the next session. Thank you very much.